Let's understand logarithms in this video. Have you ever struggled to multiply very large numbers by hand or to find the power that gives a number? Logarithms help with exactly that by turning multiplication into addition and hard powers into simple numbers to work with. First, let us recall indices or exponents because logarithms are just the reverse idea. For example, 16 equals 2 raised to the power 4. So 2 is the base and 4 is the exponent or index. Another example, 64 equals 8 squared. So 8 is the base and 2 is the exponent. Now imagine we want to multiply 16 by 8. Directly this gives 128. But using powers we write 16 as 2 to the power 4 and 8 as 2 to the power 3. Multiplying these, 2 to the power 4 times 2 to the power 3 equals 2 to the power quantity 4 plus 3. So the multiplication became addition of exponents, giving 2 to the power 7, which is 128. Similarly, when we divide 16 by 8, we write 2 to the power 4 divided by 2 to the power 3 equals 2 to the power quantity 4 minus 3. That gives 2 to the power 1, which is 2. This idea inspired John Napier and Henry Briggs to make the idea of logarithms, to make hard calculations easier before calculators existed. Now, what is a logarithm in simple words? If x equals a raised to the power n, then log base a of x equals n. So the logarithm gives the exponent. For example, since 16 equals 2 to the power 4, log base 2 of 16 equals 4. Or since 64 equals 8 squared, log base 8 of 64 equals 2. So writing a power or writing its logarithm are equivalent ways to tell the same fact. Let us learn the main laws of logarithms from these rules of indices. First law, the product rule. If you multiply two numbers, the log of the product equals the sum of their logs. In symbols, you would say log base a of xy equals log base a of x plus log base a of y. Second law, the power rule. The log of a number raised to a power equals that power times the log of the number. So log base a of x to the power m equals m times log base a of x. Third law, the quotient rule. The log of a quotient equals the difference of the logs. So log base a of x divided by y equals log base a of x minus log base a of y. Also remember, log base a of 1 equals 0 because any base to the power 0 gives 1. Let us solve some examples to make these clear. Example 1. Find log base 2 of 512. Ask what power of 2 gives 512. 512 equals 2 to the power 9. So log base 2 of 512 equals 9. Example 2. Find log base 8 of 1 divided by 64. Write 1 divided by 64 as 64 to the power minus 1. And 64 equals 8 squared. So 1 divided by 64 equals 8 to the power minus 2. Hence log base 8 of 1 divided by 64 equals minus 2. Example 3. Log base 5 of 25 equals 2 because 5 squared equals 25. Example 4. Log base 25 of 5 asks what power of 25 gives 5? And 5 equals 25 to the power 1 divided by 2. So the log equals 1 divided by 2. This shows swapping base and number gives reciprocal exponents for these cases. For example, log base 2 of 8 equals 3 and log base 8 of 2 equals 1 divided by 3. We also use common bases often. Base 10 where log means log base 10 and base e around 2.718 which we write as ln. Finally, using logs to solve equations with the unknown in the exponent is simple. For example, solve 3 to the power x equals 5 by taking log of both sides to get x times log of 3 equals log of 5. So, x equals log of 5 divided by log of 3. So what do we learn from this? Logarithms turn powers into simple numbers, change multiplication into addition, and make solving for exponents easy. Let us quickly remember. Log gives the exponent, product becomes sum, quotient becomes difference, and powers bring down as multipliers. Thank you for listening. Keep practicing these ideas on example problems and do explore more lessons on EduRev for clear explanations and more practice. Keep learning, stay curious, and try one more logarithm problem now to build confidence.